Well, thanks for the invitation to speak here. I was asked to give a talk that I was supposed to give in Berkeley 2 years ago, but I didn't turn up there, so I'm going to give it now. If they record it, they can show it at Berkeley, maybe. I've updated a little bit, and I have much less time than I had in Berkeley. Okay, so I'll try to survey some aspects. Okay, so for me, the interest in what has become known as thin matrix groups or thin orbits is the study of Diophantine equations, where we try, and you'll see examples, especially tomorrow when I talk about some cubics. We're trying to understand the integer solutions to some Diophantine equation. There are very few, and we want many solutions, not few solutions. And if you want many solutions, there are very few techniques to produce solutions. One is the so-called Hardy-Littlewood circle method, which requires a tremendous number of variables, and when it works, it's very powerful, but it's very limited when it works. If you have few variables, then the only real tools to produce solutions is algebra, or ideas from algebra. In particular, if you have some way of making new solutions from old solutions, like a group. So I'll start with the assumption that I have a way of making solutions to an equation. There's no equation yet, but it'll come quickly. So let's assume we have a group of polynomial morphisms. They needn't be linear. So these are maps, invertible maps of affine space into itself. And I take the orbit of a point under the group. The group should be infinite, otherwise I'm not going to produce that much this way. I take the Zariski closure of the orbit. In any example, this will not be the hard part of the problem. And then this Zariski closure, you can easily see, will be gamma invariant over the complex numbers. So I get some equations which are actually defined over Q. There's an issue of Z and Q, don't worry about that. And then I take the integer points, and now the group acts on the integer points, and it decomposes into gamma orbits. It could be they're infinitely many orbits or they're finitely many orbits. And the case where there are finitely many orbits for the integer points on this variety, so I've now got a set of equations, and I've got integer solutions, which are abundant because I can move around with gamma. The case where there are only finitely many orbits, and that will be the linear theory that you'll see in a minute, or the non-thin case. The case that there are only finitely many orbits, then I've lost no information, essentially. If I want to study the integer points on this variety, I can study it orbit by orbit. The thin case is where there are infinitely many orbits, and then you could imagine that each orbit is tiny and not telling me much about the integer solutions. But there will be cases where this still will be decisive, and that's kind of interesting. So that's the general setting. I have these morphisms. It looks like dynamics, but the most important thing about these morphisms is they're invertible on affine space, and they preserve integers or S integers in a number field. Okay, now in the study, so I've now converted the problem for a second to a problem of Diophantine analysis of an orbit, rather than of the usual thing, which is integer solutions to equations. If you're studying an orbit and you're trying to understand some Diophantine properties, there are a number of tools that have been developed over the last 15 years, or maybe 20, 25 years. But I want to single out two really important tools in this analysis. And one is strong approximation, and we saw this discussed in the first two lectures today in some examples and in some great generality. For me, I take the low road. This just means I reduce mod Q, nothing fancy, no p-adics yet. So I just take the orbit, I reduce it mod Q. I will land in VZ mod QZ, and I want to know that I'm rich. Now, because I have an orbit, and the orbit was an orbit of a group, it's easy to see that the morphisms which I started out with, you can remove a finite set of primes. The morphisms that I started out with actually reduce to an action on this finite set, and they act as permutations. So if I want to understand strong approximation, which is how rich is the reduction of V modulo Q, or the orbit modulo Q, it becomes a group theoretic question, a highly non-trivial group theoretic question in this setting of what is this permutation group, which is acting now on this solution set V, on this finite set. Is it transitive, for example? Does it move me from any point to any other point, or what are the components of this action? That's strong approximation in this form, and if you want to serve, or if you want to even formulate local to global principles, you need to understand what this image is. And if you have these morphisms which are nonlinear, this is a highly non-trivial problem. Now, there's a strong version that goes with this, which is the title of this meeting, I guess, strong approximation or quantitative strong approximation. I'll formulate what it is and where it comes from in a second. But one way to think of it, and it's the way I like to think of it these days simply because of a problem I'm thinking about, you could ask, if this maps onto, what is the minimum lift? How small is the minimum lift that if you want to estimate the smallest lift, that's a quantitative statement. And for that, you would need something like a spectral gap. Let me say a word about the spectral gap, and I'm waiting for this guy's lecture tomorrow where it seems like he's removing the spectral gap, because I've always is everything. So we'll see tomorrow what he's doing. I'll wait. Anyway, I should say this, that when you do an ordinary sieve, a Brun sieve, on the line, which is where Brun invented it and where most sieving is done, the idea of the sieve is to count primes up to x. You count numbers up to x and then remove the numbers which are divisible by 2 and by 3 and then add back the numbers divisible by 6. So whatever you're doing, you better know how many integers less than x there are which are congruent to 0 modulo d, and you want a good approximation to that. And if you're on the line, the number of integers less than x which are congruent to a modulo q will be x over q plus O1. Never forget that O1. Because that's the source of many mistakes. And that's accurate as long as q is less than x. If q is much bigger than x, that's quite useless. So that is a very easy count that nobody even internalizes. But imagine you on a non-commutative group, something like a tree, and you want to do this argument where you're counting the number of integers which are congruent to something modulo something in a ball. The number of points on the boundary is as big as the total number of points in the middle, unlike the line. And then it's highly not obvious, it's not at all obvious, that the number is basically the total number of points divided by, so to speak, the volume times the number plus something smaller. And the spectral gap, which was described in terms of a drunkard walking or something, is very powerful in that. So this quantitative strong approximation is very important, and in the context of thin matrix groups, that's the thing I want to highlight in this lecture. So this lecture is going to be about the linear theory. The morphisms are all linear. Tomorrow's lecture will be about a nonlinear. It's linear or affine linear, and it helps you a lot. So the theory that has become, I think it's got a firm foundation now, is the linear case. So the group is acting affine linearly. You can double the number of variables. It's acting linearly. So I have a subgroup of GLNZ. I take the Zariski closure of the group, which I'm assuming we can determine easily. All answers should be given in terms of this linear algebraic group. It's got a dimension. We know what we're talking about when we talk about G. But when we talk about a discrete subgroup of GLNZ, we know that's arithmetic. It's much more subtle. And then gamma is contained in GZ, or maybe you want to introduce some denominators. I'll skip over that point again. So I'll say gamma is arithmetic. It's not the exact, but it's essentially the same usual definition. If it's finite index in GZ, just this reflects my first slide, and it's a thin matrix group. I've been criticized since I think maybe I popularized this term thin. Thin occurs in Sarah's lectures on the Mordell-Weil theorem. In another context, thin subsets. Thin occurs in, I've been told, finite group theory. There's some very standard notion of thin group. So I think the right word to say is thin matrix groups. So we're talking about matrices. And that's what we're talking about here. So gamma is arithmetic if it's finite index, and then the orbits will be much more classical problems. And gamma is thin, then it's a more exotic problem. So we take the orbit. Assume that of the algebraic closure, the orbit is a closed subset of affine space, then the stabilizer will be a reductive group, and we're in a homogeneous setting in that case. And then we understand, and this is acting linearly, we have a right to ask that we understand the Diophantine properties using arithmetic groups, and another tool for strong approximation using automorphic forms. So famous theorem of Borel and Henry Chandra says that if G is semi-simple and H is reductive here, that the Z points will consist of finitely many orbits. It's a generalization of an old theorem of Hermite and Minkowski for quadratic forms. So this is the arithmetic case, and the study of the orbits is tantamount to the study of all the Z points because there are only finitely many orbits. And it's, as I say, the usual problem, usual kind of problem. The strong approximation for arithmetic groups is a very well-studied subject. You just need to look at, say, Rapinchuk and Platonov's book. One of the highlights is to describe strong approximation for arithmetic groups. What happens when you reduce modulo P or you move into the Adels? What's the closure, as Ali Reza was explaining earlier? That's well understood, and it's very much linear and group theory. The quantitative question in the arithmetic case, which is very much used in all Diophantine analysis of the type that I have in mind, all use the Ramanujan conjectures, which, let me just remind you in this lowbrow version, is we are in an arithmetic case, so GR over gamma, or maybe if you work adelically, this is a finite quotient, and you take this Hilbert space, you decompose it under the right regular representation, and you ask which representations come up. And the theory of automorphic forms is no more, no less, at this side of the subject of understanding these. And you would love to know that the only guys besides a trivial representation that comes up in this decomposition, this is finite volume, so the trivial representation occurs in that L2 decomposition, is that everybody else is what's called tempered. That's the famous Ramanujan, general Ramanujan conjectures, which are false in this generality. And formulating them is quite tricky. But we do know in these cases very strong bounds towards Ramanujan. And it's not an issue of saying, oh, we can prove Ramanujan for holomorphic forms. That's interesting, but useless to us, because we have to face all the representations. So it's like with the Riemann hypothesis. If Selberg tells you there's a positive proportion of zeros on the line a half, that's useless. The techniques are brilliant. But the result, I've never seen that used. A much more powerful theorem is there are no zeros off the line. Well, we don't know that. But if you told me the zero-free region is this, that's useful. So it's not what's there on the line and tempered, it's how well you can show something, all the exceptions, how close they are to being tempered. And those control the spectral gap very effectively and this random walk, and they are critical in any kind of sieving, if that's what you're after. In the thin case, this volume's infinite, and we don't and all the tools of Langland's program, if you like something like that, or algebraic geometry, are just not available. So you might even worry that why on earth would there still be some remnant of the Ramanujan conjectures? And I think we owe it to Lubotsky, actually, that it is there. He has a student called Yehuda Shalom whose thesis sort of started this dream, let's say. So the key tools are strong approximation, and in the thin case, one could ask, so the thin case remembers I'm infinite index, so I'm now outside the arithmetic case, and this is perhaps exotic, but I will spend the second half of what time I have to try ask, are thin groups ubiquitous? Anyway, there's a great insight here, pursued primarily by Weisweiler, that suppose I'm a subgroup of SLNZ, gamma, and it's Zariski dense. You're not asking much to be Zariski dense. You can't help yourself to be Zariski dense. If you take two elements, you're going to be Zariski dense. So suppose I have a subgroup which is Zariski dense, but infinite. Typically, it might be infinite index in SLNZ. So it's Zariski dense. And now I reduce modulo a prime. When I reduce mod P, I'm into a finite group. So perhaps the fact that I was deficient in being infinite index is now forgotten. And that's the theorem. So if you're arithmetic, this is well known, that you reduce SLNZ to SLNZ mod QZs onto. And the remarkable theorem, first of Matthews, Weisweiler, and Wasserstein, which I guess did use the classification of finite groups. Norrie gave a proof which is quite effective and very powerful and avoids that. Larson and Pink gave yet another proof. And it says that in this just Zariski dense setting, that there is a finite set of bad primes, which you would have anyway, where you're not onto. It's a finite set of primes, you can find them, such that outside that finite set of primes, you are onto. So strong approximation holds anyway. So even though you're deficient, you still have strong approximation. So that opens the door to do some Diophantine analysis on a thin orbit, because at least in this linear case, I know what I'm hitting. A fundamental fact. This is really a fundamental fact for everything that's done afterwards. I don't know your exact involvement here, but he does acknowledge you for, I don't know what, this is Weisweiler in one of his papers, for maybe asking the question. Anyway, it's a great insight. And the theorem here is we understand this in general, especially if G is both semi-simple and simply connected, like SLN. And if it's not, then you might have to pass to a simply connected cover, like with an orthogonal group, to a spin cover, and then everything is restored. So we do know strong approximation for thin groups. And that's an old theorem. That's from the 80s. The question of how to capture the spectral gap or some form of Ramanujan in the setting where arithmetic is gone or where G mod gamma is infinite volume, the whole point of automorphic forms is that G mod gamma should be compact or finite volume so that there aren't that many automorphic forms. And then you classically show something's automorphic because the space is finite dimensional, maybe. But the minute you take G over gamma infinite volume, you're doing some kind of weird analysis. This is a big space. There are too many periodic functions. But still, the arithmetic apparently exists. So how do we form a form of super strong approximation in this setting? You take a set of generators for gamma, it doesn't matter what. You make them symmetric so that I'm about to make a graph, which is an ordinary symmetric graph. And for each integer greater than or equal to 1, I look at the kernel. So gamma is a subgroup of GLNZ. I look at the kernel, gamma Q. It's finite index because it's mapping into a finite group. And I form the following Cayley graphs, or congruence graphs I prefer to call them. Gamma over gamma Q. Gamma Q is normal, so this is a finite group. The image will be, for outside of a finite set, it will be by Weisweiler. We'll know what it is, basically. So this is the Cayley graph. The vertices are the elements of the group. And this set is chosen one for all. The property I'm about to highlight does not depend on the choice. It depends in the epsilon. A different epsilon might work, but the existence of an epsilon or an expander will not depend on the choice of S. So this is a well-defined notion. And I want these graphs whose number of vertices is growing, but whose regularity, each guy is joined exactly to, I just joined by the generators, as you do in a Cayley graph, each guy is joined to cardinality of S neighbors. The graph, by definition, is connected because S is generating. And I want these graphs to be an expander family, and I think Ali Reza sort of defined an expander this morning, and probably you all know what it is. But it's a remnant of Ramanujan. It's spectral gap if you look at the nearest neighbor Laplacian. All right, so we want that to be an expander family. And it's a remarkable and one of the great achievements in the last 12 years or even longer that this is a fundamental theorem, and it's now used left, right, and center for thin groups. And this is the main theorem that Ali Reza put up as a conjecture. I suspect he put it up as a conjecture here because I'm exaggerating a bit. Q should be square free here, and in general, maybe not quite settled for if Q is not square free, which is important in some applications, but let me slough over this point. And this is the theorem. It has a tremendous chronology. Xu and I gave a proof of Selberg's theorem, which was purely combinatorial and counting, and used a little bit of group theory, which is at the heart of the endgame of any of these proofs. Gumbert, in his thesis, following Yehuda Shalom's thesis, actually, proved the first examples of this theorem. Helfgott made a very major breakthrough in SL2 in his A times A times A theorem, which was really changed the subject because it allowed you to do some counting purely combinatorially rather than the way that we were doing it before, which was to use some Diophantine analysis. So it was an internal counting. And this internal counting was based on the sum product theorem of Katz, Tau, and Bogan, as a key input. So combinatorics entered here. Quickly, Bogan and Gumbert invented this flattening argument that we'll see more of, which is at the heart of all further arguments. All these are for reductions modulo a prime. Bogan, Gumbert, and myself were able, since we needed to serve, were able to deal with arbitrary Q, square free. It's much more complicated. And then the general case of, this was all SL2. The general case of an arbitrary Chevrolet group was done by Piba and Szabo and Brouillard, Green and Tau almost simultaneously. It's a funny world we live in. This was posted by Piba and Szabo, and then within 3 hours they posted their solution, which was very similar. And that's not surprising, because they both were based on an insight of Lushovsky, actually, which stimulated it a year before. This is the general case for prime, and Varju in his thesis he found a simpler proof of this, and he was able to deal with SLN. The final version of the theorem as of a couple of years ago, and perhaps it's a little more elaborate right now, but this is good enough, is a theorem of Salehi and Varju, which is an if and only if. It was stated this morning. Let me review it. It's a beautiful theorem. It's a fundamental theorem. And that is these form the congruence family are an expander family if and only if the connected component of the identity, everything's in terms of the Zariski closure, as all good theorems should be. Gamma's gone, so it's just about G, the Zariski closure. If its connected component is perfect, then it'll form a expander family, and otherwise not. And as I said in his lecture, if this fails, then it's not difficult to see that you can't have a full expansion property. So the one way is easy, the other way is extremely involved, and many people have contributed to it. So that's the basic expansion theorem. In some of this Diophantine analysis on an orbit, the general theorems that are proved all are using, when we look at G mod gamma, if it's infinite volume, let me state it this way. If I look at GR over gamma, it's infinite volume. That's this thin situation. We don't know how to do the analysis in higher rank. This is a major unsolved problem, to understand how to study counting, Archimedean counting in infinite volume, except in rank 1, and even in rank 1, it's mainly only done in hyperbolic n space. So in a hyperbolic n space, there is a theory. Starts actually with Lax and Phillips, who I used to work with. Ralph Phillips was a great guy. He always wanted to do scattering theory, because he really wanted infinite volume, because that's where you scatter. And that's where he could take his theory with Lax and transfer it to hyperbolic space. So he was very interested in infinite volume always. I always told him there's no number theory in infinite volume. Unfortunately, I have to withdraw that now, and I hope he appreciates that. Anyway, the infinite volume higher rank is really open. So in this case, there's a paper of Bogan, Gumbert, and myself, which transfers this combinatorial gap to an Archimedean gap in the geometrically finite cases. And even that's not enough, so sometimes we have to transfer it to what's called the thermodynamic formalism developed by people like Lally, in order to make use of this spectral gap if you want to sieve. And that's, in the semi-group case, this has become even more important. And this Archimedean theory has been developed by Kontorovich O, Shah, O. Wintner, and McGee O. Wintner, all of which are in this hyperbolic space setting and critical ingredients besides just the spectral gap. But one can transfer, and that's what these theorems say, these ideas that are in the proof of the combinatorial expansion property to this Archimedean setting. All right, there are many, many applications of the fundamental expansion theorem besides to number theory. And let me just review that for you quickly. So, of course, it was developed for this affine sieve that Bogan, Gumbert, and myself, and Salehi and myself have developed in complete generality. But it has found many, many other applications, of course, none of which we had in mind. One is sieving in groups, and I think Mary will speak about this. So some aspect was observed by Riven, but Lubotsky and Meiri were actually able to solve group theoretic problems by actually sieving within the group and using this spectral gap. So we'll hear more about that. There's some works of Dunfield and Thurston about making random 3 manifolds and asking about whether their Betti number is 0 or not, first Betti number. And they show that in their random model, the random 3 manifold has 0 Betti number. You're not going to produce a positive Betti number by just the random guy doesn't have this property. the spectral gap allows you to take their argument and show that the probability of so where they're saying the probability is small, you can show the probabilities are exponentially small, naturally a consequence of a spectral gap. And that's work of Kowalski. One of the most striking uses of a spectral gap is by Lakenby in the arithmetic case, and that is there's something called the Hagar genus, which is the way you split a hyperbolic three-manifold along a surface, and the Hagar genus is the smallest surface under which you can realize the three-manifold as a body on two sides of it, and that's called the Hagar genus. And understanding the Hagar genus, it's known that any three-manifold has the genus of any hyperbolic three-manifold is bounded by a constant times its volume. What Lakenby showed is that if you an arithmetic congruence using the number theory and using lambda 1 for a hyperbolic three-manifold, showed that there are examples. There's a tower through a congruence tower. Always the Hagar genus grows as fast as the volume. It's very hard to understand the Hagar genus, and this uses lambda 1. It's quite remarkable. And here's an amazing paper, and let me tell you why. It takes Lakenby's argument, it's 2 pages, maybe 3, I don't know. And it says, every hyperbolic three-manifold is thin. So Lakenby could only work in the arithmetic setting because he was using this fancy automorphic forms to get lambda 1 as positive. But there's the old theorem of Selberg, long before Mostow, that you have local rigidity for lattices in SL2C, so you can always conjugate your lattice so the entries are S-arithmetic numbers in some number field. So every hyperbolic three-manifold is the gamma is a linear thin group. And because we have an expansion for thin, this is now completely general. It shows you how you can free yourself from arithmetic to general. So it's the same theorem. There's a lovely theorem there was a conjecture of Gromov about distortions of knots. He made this in the 80s, whether any knot can be brought into a position where it's got bounded distortion. He didn't think so. By isotoping, by transforming the knot into the distortion is the maximum, once you realize the knot in 3 space, it's the maximum of the distance along the knot to the underlying space distance over all pairs of points inside on the curve. And you might think that if you have a very complicated knot, it has to have some big distortion. And that was proved by John Pardon in his thesis here at Princeton, undergraduate thesis a few years ago, by constructing examples. And soon after that, he had a big idea. And soon after that, Gromov and Guth gave us a completely different proof that there are knots with arbitrary larger distortion, and the key ingredient was to relate the distortion of you have a three-manifold which is realized as a branched covering of the sphere over a knot, and if that three-manifold has a spectral gap through its volume relative to its volume, hyperbolic three-manifold, then they prove a lemma, which is not so different to Lakenby's actually, a lemma which says that the distortion is at least some constant times lambda 1. Lambda 1 times the volume. The volume gets big, lambda 1 is not small, that's a spectral gap. So they give a completely different construction of knots with larger distortion. I mean, they have many ideas, but one idea is the spectral gap. Similarly, if you take curves constructed as towers, which may or not defined through congruences, and this comes up in monodromy all the time, and you want to know what the gonality of this curve is. That is, and now it sounds similar to the three-manifold situation. You want to know, if I give you a complex Riemann surface, what's the minimum degree cover it can be realized of P1? So by Riemann rock, if it's genus G, it's at most G plus 1, and the gonality is the minimum degree. So if you have a hyperelliptic curve, the gonality is 2. If you give something like the modular curve, which nobody knows to write equations for, because this theorem reflects that you won't be able to write down these equations, because the gonality grows linearly with the genus, just like this Hagar grows linearly with the volume. And that uses Selberg. So you need a lambda 1 there. And there are even applications of these thin groups to optimal quantum gates. Okay, so I hope that indicates to you that this spectral gap theorem, the main theorem, is a fundamental theorem, And so I want to spend my last 15 minutes here in describing or analyzing or discussing, is the notion of a thin group interesting? After all, maybe, I hope Elena convinced you that the Apollonian packing is worth looking at. That's, what did she call it? The quintessential thin group. Okay. But do these things come up? Do you have to actually face them? Are there situations where you may not know whether you're thin or not, and you have to apply these steroid theorems in order to achieve what you're after? And I became interested in this because I was going to give a lecture, and I decided I wanted to look at a few examples, and I couldn't decide what was going on. And then I began to realize that this is not an easy question. And in fact, the first sobering experience, which I learned from Igor Rivin, was the following. That suppose, remember, so the rule here of thin, if you're in automorphic forms, I always tease this guy because when we used to discuss things, he would say, take SL2Z, and he'd tell me, that's a group, the free FZ2 free product Z3. And I didn't know that. To me, SL2Z was the 2x2 integer matrices. So everybody has a way of thinking. So he might think of the group as being finitely generated. I think of it as globally. In this thin situation, we are going to always be given the group in terms of generators. So you have to go to the kind of mathematics where a group that you're looking at is born in terms of generators, as it was with the Apollonian packing. There were a few moves you had to make, and you have those moves, and that's all you can do. And then you take the group generated by that, and then if you think you know what the group is, watch. So there is no decision procedure to take in 7 elements in SL2Z cross SL2Z, and it will output whether this group is finite, or whether it's the whole group, whether it generates a whole group, or for that matter, whether it generates a finite index subgroup or not. Is it thin or not? This is an undecidable problem. That doesn't mean that any example you can't do it. It's just the standard. You can't give a universal machine can't answer this question. So if you're given your group by generators, you may be looking at this and you may be stuck for years before you can decide if it's finite or infinite index. I'm going to give you some very topical examples that people have wondered about and still don't know the answer to in a second. I should emphasize that if the group were finite index, just like in the Diophantine problem, if I give you a Diophantine equation, I say, has it got a solution? If it's got a solution, you can always convince me by exhibiting it. I won't argue if you give me a solution. This is very similar here. I can convince you that I'm finite index, or if, say, in the congruence case, I can convince you I'm finite index. So if I'm SLNZ, I know standard generators. You give me your few transformations that are generating your group, and you think it's everything. Well, you start multiplying the matrices, and when you hit my generators, I know we've won. But you might start multiplying them on a computer, and you don't know when to stop. Which certificate? No, I'm just saying, there's no way, this is undecidable.
No. If it's congruent, I'm just saying you just do the moves. Yeah.
But I don't know. So they are fake SLNZs. No, the answer is there is no algorithm. I'm saying if it were congruence, and I found these by some fluke.
No, because of undecidability, there can't be a non-undecidable.
Yes, okay. That's correct.
But Peter, you don't know that in general.
I don't know it in general. Right. But I think all people. I don't know it, but I'm just saying if I can't do this, and for me that's you're right. It might be different at higher rank, where the congruent subgroup property is true, there may be. It's not solved. I was just looking at some examples. Let me continue with some such examples in a second. All right, so if you're a true group theorist, then the group is given to you by generators.
Wait.
You can't, but I'm saying, the analogy is supposed to be this. Suppose I give you a Diophantine equation, and you ask me, has it got a solution? I come back with a solution. Game over. If you give me a group, and it happens to be a congruence subgroup, and I come back and find the generators in terms of your generators, game over. That's all I'm saying.
The question is, what's a nice class of thin groups which can't be certified?
Watch. I don't quite know the answer, but let me frighten you as we go along. a true group theorist would say you choose your generators at random. So if you take S, L, and Z and take A and B at random, you will get a thin group. So the random group is thin, and this is a theorem of Ayun and Fuchs and Riven. So the random subgroup, you take A and B at random in any sense you want, will be both free and thin. So that's this theorem. But groups are not chosen by choosing random generators unless you're really a group theorist. I want to give you an example where if you open any quantum computation book and become very interested in this, you'll see 2x2 matrices with names on them. Adamard matrix, Pauli matrix. The group generated by these is what's called the Clifford group, which actually you're probably familiar with. It's a finite index subgroup of projective unitary group. And they want to make gates which will be in every quantum computer. And to be a universal quantum gate set, you need to be topologically dense in this group. And this is a finite group, so it's not topologically dense. Greater than 3, you will be topologically dense. But are you thin or are you arithmetic? And it turns out in all the books, there are exactly 4, I show this in the letter, based on some actually quite nice computations of Serre, that in the hardest case, I should say, that the group, you're just asking these groups generated by this, is a finite index in the natural S arithmetic group or infinite index? And the answer is it's arithmetic if and only if it's one of these 4. In this case, it's called the pi/8 gate, and it will be in any quantum computer. This is what everybody's trying to build. It happens to be a golden gate in my language. So it's interesting that they're making gates. So, of course, they're choosing generators, and you're unitary because that's how quantum computer works. All right, so the issue of a group given by generators is an interesting one, and I want to end with this monodromy groups. That's the most interesting case of groups given by generators. But I want to remind you of a theorem of Winberg. I think his view here was that this was a failure. He was trying to make non-arithmetic subgroups in hyperbolic n space. And he was not able to do it. He showed that reflection groups will never give you arithmetic groups. And in fact, what he showed was, suppose you take a quadratic form in n variables, rational, and it's hyperbolic n space, and you look at the group generated by hyperbolic reflections, this normal subgroup which are given, the subgroup of the group generated by all hyperbolic reflections, and he asked whether that normal subgroup is finite or infinite index in the group GZ, in the group of all automorphs. So he's asking whether this is a thin group or not, even though it's potentially infinitely generated. And he shows, except for finitely many cases, and these have been classified by Nicolin, they're used in K3 surfaces, this is always infinite index. Quite remarkable. And he's got a certificate for infinite index, and that's because if a group's generated by, this is a generalization of Coxeter's theory from Euclidean reflections to hyperbolic reflections, there's a canonical fundamental domain that you have when your group's generated by reflections. So it's a way of showing something is infinite index. As I said, he was trying to construct non-arithmetic groups by these reflections of for arbitrary n, and he wasn't able to. That was later solved by a very beautiful short paper by Gromov and Piatetsky-Shapiro by actually gluing along a hypersurface 2 arithmetic groups. So I turn to monodromy groups because these are groups which arise in cohomology. In cohomology, you really want linear algebra. So maybe you have a family of varieties, and as you move around the base, you take some cohomology group on a typical fiber. They're all the same outside your bad set. And when you go around and come back, you start with an integral cohomology class. When you come back, you come to a change of an integral cohomology class. So you have something automatically in GLNZ. So for free, you get subgroups of GLNZ. And the monodromy group family is, in the algebro-geometric world, defined to be the Zariski closure because nobody wants to actually say what this group is. It's too complicated. And miraculously, in many of the calculations in algebraic geometry, you only need to know the Zariski closure in order to make your conclusion. That's what this steroid theorem says. You only need to know this Zariski closure to have super strong approximation. So it's, in that way, a good thing. But I think people, okay, I always repeat this story. I had a bet with cats for 25 cents about whether all monodromy groups from algebraic geometry are thin or not, if they're simple. In fact, this question was first posed in a paper of Griffiths and Schmidt on variations of Hodge structures, and they actually seem to believe that every monodromy group that comes in that setting will always be arithmetic. In fact, one reason they believe that is the only time you could certify what the group was was when it was finite index. So the only examples known were arithmetic, and the other ones, well, who knows? I think that's part of the misunderstanding, perhaps. So here's an example which contains all the difficulties, and one that will relate to my lecture tomorrow, which will be about Payne-Lavey indirectly. And that is, I'll take the hypergeometric Fn minus 1. This is a good example of computing monodromy. So it's a linear ordinary differential equation of order n. The parameters are rational in order for this to be an algebrogeometric kind of problem. This is the nth order equation. And you can write the solutions down by Frobenius's method, and they are these hypergeometric functions. So you have z to the 1 minus beta I. This means leave out the I thing, and this f is your power series expansion with these generalized factorial coefficients of how all hypergeometrics look. And this set with I equals 1 to n give you your n linear solutions around a point. And then you, with a hypergeometric, it's got singularities 0, 1, and infinity. You go around a cycle, you come back. So you start with a basis, you come back. When you come back, you have a linear change of variable, and that's your monodromy representation, as introduced by Riemann to explain Gauss's work on F2-1s using monodromy. Cats at monodromy.com, by the way. But Riemann invented monodromy. All right, so here's a simple question. What's the monodromy of the hypergeometric? I'll assume this is because the numbers are rational. The actual matrices, when you go around a cycle, they're just two cycles because it's a free group on two generators. So you just get two matrices in this integral matrix group. I'll assume everything's integers in whatever I say here rather than integers in a number field, though I presume this can be generalized. There's a beautiful theorem of Boykers and Heckman which computes the Zariski closure of the monodromy. In particular, in the cell-dual case, it's either a finite group, in which case they show you what it could be, and there's many sporadic examples up to n equals 8. And once n is greater than or equal to 9, there's only one finite group that appears, which is the symmetric group, or the alternating group, I can't remember, one of the two. And that's the list of finite monodromy groups. Or, a beautiful theorem, remember it for tomorrow, it's all hypergeometrics which are algebraic functions of their variable z. They classify, generalizing Schwartz's theorem about F2-1, which hypergeometrics are algebraic functions of z. That's the same as saying the monodromy is finite. We'll see this with respect to Payne-Lavey tomorrow. So Venkataramana, who's here, saved me a few years ago. I was giving lectures in India, and he knew exactly what I was going to conjecture. I don't know how. And he came to me before the lecture, and he said, I want to show you something before you open your big mouth. I was going to conjecture that for hypergeometric, once you're infinite, where nobody really knows what the group is other than it's a Zariski closure, I was going to conjecture that it's always thin outside of a finite set. And he said, you might be interested in this example. Here's an example. Infinite family of hypergeometrics, all of which are arithmetic. And he might talk about it. But I should tell you that before him, I didn't even know, and I don't think anybody knew, whether SPNZ has a finite index subgroup, or congruence it would have to be, if n is greater than or equal to bigger than 2. If SPNZ has a finite index subgroup generated by two elements. So in particular, because our monodromy is generated by two cycles, one around 0, one infinity. We have these two matrices, and we're asking, is the group generated by them finite or infinite index? All right, so you were very kind. Of course, I would have just said, oh, yeah, I meant that. Okay, perhaps the most challenging one, I had a bet with cats, as I said. The bet, I'll show you, Meiri, Fuchs, and I actually won the bet. But we paid it up to the real deserving winner of this bet, who's Brav and Thomas, because their example, I think, is more interesting than ours, as I'll explain. So there's this Calabi-Yau threefold, the mother of all mirror symmetry. And the hypergeometric for that it's in 4x4 matrices, and it's got the alpha in the notation I used as 0, 0, 0, and beta 1/5, 2/5, 3/5, and 4/5. And if you go around one cycle, you get a 4x4 integer matrix, and you go around the other cycle, you get an explicit 4x4 integer matrix you compute around the vanishing cycle. And now you're asking, is the group generated by these two matrices, which by Boykers and Heckman is Zariski dense in SP4, is it finite or infinite index in SP4Z? And this stood for about, Candelas is probably the 90s. This stood for a good 15 years. Because it is thin, it is infinite index, and how on earth do you show it? There are examples that are arithmetic, and then there are techniques. But if you are infinite index, how do you actually convince somebody that something's infinite index? What's your certificate? So there's one general tool, if I may take 2 minutes, that these guys use, is ping pong. Now, with ping pong, you usually show that there are subgroups of a Zariski dense group which is free. This is they're exploited heavily by Tietz. But when you play ping pong, you always choose your players. You choose them to act very far in projective space so that they don't interact, so that you can see they're free. But when you have monodromy, you have these vanishing cycles. You got your matrices. They're not playing ping pong. So if you're not allowed to choose the players, you're stumped. But they go to a computer, and they go to projective 3 space, and they find very complicated sets which have about 10 sides, convex set, polyhedra, on which generalized ping pong is played, from which they conclude the group has to be infinite index. So it's quite remarkable. And this, if you look at Candelas et al., they have no idea whether this group is finite or infinite index in SP4Z. And I don't know that they seem to think, they obviously check numerically, and they think it's infinite index. I don't know if it actually has any physical meaning. It's Z mod 5Z, free product Z. So it's essentially free. So it's quite an achievement, and Mr. Brav owns 25 cents in his drawer. It's really the most pretty example. Anyway, let me end by saying that there's one case where I still believe, so I don't know whether thin is ubiquitous or not in the monodromy world, but there is one situation in which I'm pretty sure it is, and that is if take the hypergeometric, and if the Zariski closure is an orthogonal group, and the orthogonal group is of signature n minus 1, 1. So it's a hyperbolic space on which it operates. So it's still real rank 1. These techniques we're using, which are based on Windberg, just disappear in higher rank. Then we have a condition. We have a certificate, and Mary, maybe he'll explain it. We have a condition, this is Fuchs, Mary, and myself, which is like a Brouwer-Mannian obstruction, which is a global condition, which if you verify and something happens, it actually proves your infinite index, and we can give, using that whole infinite family. And our belief, or my strong belief, I don't know about my co-authors, my strong belief is that all but finitely many of the hyperbolic hypergeometrics are actually thin. When we prove something's thin, we don't actually know whether it's geometrically finite. We're now in hyperbolic n space. And nobody said this group, which is finitely generated, would be geometrically finite, a feature which would help you a lot. H. Park, in his thesis in Princeton a couple of years ago, was able to find one example with n greater or equal to 5, which is geometrically finite. And his proof was to find the Dirichlet fundamental domain and see that things closed up. It's got like 56 sides in hyperbolic 4 space. And it's the only example. It's Our condition shows it's arithmetic, but he was able to show that it's geometrically finite. So I have no idea in this SON1 cases whether the monodromy groups of hypergeometrics, of which there are many, are geometrically finite or not. And since this is a special here in hyperbolic geometry, I was hoping somebody might get interested. Thank you.